Thank you all for joining us on today's webinar, Fire-Rated Expansion Joint Assemblies, Code Standards and Inspection Types. We're looking forward to a great presentation from Steve Cooper. So just briefly, Steve Cooper is Vice President of Special Development and Training for Building Safety Products with Valco. He has extensive experience in manufacturing operations, sales, and product design. He works with architects and engineers to develop proper specifications and designs using life safety and fire-rated products on large commercial and institutional projects. Steve is the chairman of the Expansion Joint Committee for the International Fire Stop Council, and he has served on several technical committees for codes and standards. Steve is a graduate of the Oklahoma State University School of Engineering Technology and Tabor College School of Business. Steve, thank you for putting this together for us and for presenting. I'm going to turn it over to you now.
All right, thanks, Aaron. Appreciate it. So I'm going to put a face with the voice there so you can kind of imagine me talking away as we move through here. So I'm going to turn the camera off now and let us get started. All right, so yeah, this is the Fire-Rated Expansion Joint Assemblies, Code Standards and Inspection Types. This is an AIA and ICC provider course, and the number there is 38200. It is 1 hour AIA CEU credits for health, safety, and welfare, and it is also International Code Council 0.0875 credits towards your continuing education. So it is copywritten, so please don't make copies of this in any form and use it in any kind of publication without some written approval from somebody authorized at the International Fire Stop Council. So our learning objectives, the key learning points are going to be, we're going to learn about code requirements in accordance with the International Building Code, the most current 2021, and the test standards that apply within that are referenced to that code. How the inspection processes work for fire-rated expansion joint systems, and then the different kinds of systems that you're going to see and experience in the field. There are quite a few varieties, and then how to identify some field issues. So we're going to take some good looks at some installations and that are good, and then some that are not so good, for sure. So this is very code driven at the beginning of this, so a lot of text, not a lot of pictures in the beginning, but it does get to be a bit more pictorial, and so if you're a visual learner, that'll pick up a little ways into the presentation. So I want you to understand just the general process. We call this compartmentalized fire protection, and it's required by the International Building Code. And so the building code mandates specific fire test standards. So the code says, hey, this is required, and then it says this is how you know what to do with these test standards. And then to prove that you have done that, there are compliance documentations called listings that are supplied by the test laboratories for the manufacturers for submittal documentation in a project. Project designers, generally architects or engineers, they specify specific manufacturers because that's what the listings are. They're associated with a specific manufacturer, and so you can have multiple manufacturers or whatever, but they will identify these by manufacturer in their plans and specifications project documents. So inspectors will be using this documentation, these plans and specifications from the architect, from the engineers. They'll be using documentation from the factories that manufacture these products and test laboratory information. And hopefully at the end of the whole thing is that what we end up with is a safely compartmentalized building that limits any kind of casualties or any kind of issues in the case of a fire or smoke or toxic gas and things related to these. So I'm not going to dive into the deep history. If you're in the fire industry, you probably already have heard of this one, but the MGM Grand Las Vegas in 1980 is really the structure fire that kicked off a lot of compartmentalized fire protection in many different categories: fire stop, expansion joints, and other kinds of areas in there. But there was a lot of loss of life. This was a bad incident, and a lot of things were discovered that led to a lot of progress that we see now. So what we determined out of that through a study from John Hall Jr. from the NFPA Fire Analysis and Research Group is that smoke is the problem. It's generally not the heat or the fire, the flames that cause the fatalities. It is the smoke, and toxic gases would be related to smoke. You can't really see through smoke, right? It gets pretty thick. Here's the deal. It's the speed of smoke, and most likely people underrate the how fast smoke travels. Now, it is not moving at lightning pace. According to this study, it moves 120 to 420 feet a minute. So you might not be able to relate to that, but that's 3 to 5 miles an hour. 3 to 5 miles an hour. That's a pretty good walking pace to a jogging pace for most folks, and that's if you're on a treadmill or in an open environment. But if you put that in a building that has hallways that are smoke filled with people trying to escape, it is just not practical to move that fast. So smoke overtakes folks pretty quickly in a structure fire. So that's the danger. So how do we address that? Well, compartmentalizing the structure is the method that has been kind of developed over time after seeing how these things work. And so what you can see here is a building plan, and it's segmented off into 4 segments. And those blue lines, and there's some red lines in there mixed in with it. The blue lines are smoke partitions. The red lines are fire barrier walls, and then there's some mixtures that are fire and smoke as they overlap. We'll explain all that as we go along, but it's essentially this building has been broken up into 4 segments that each have their own way of egress out of that without having to cross over those barriers into other segments. So we've compartmentalized the structure in place. So that's all great until you start slicing the building apart through those openings or punching holes in the walls for fire stop and things like that, electrical equipment, HVAC, plumbing, all those different kinds of things, start puncturing holes in what was meant to be a protected zone, a fire or smoke protected element. Well, in the case of an expansion joint in a building or a seismic joint in a building, we'll use those sort of interchangeably. What you have is 2 completely independent structures, independently supported and separated by a small opening, maybe an inch or 2 or 4 inches wide, even up to larger openings can be 24 inches or 48 inches. They can get quite large in large seismic zones. But they're 2 independently separated structures that have an opening across a fire-rated component, which could be in the floor, it could be in the wall, it could be in the ceiling or the roof as it cuts through there, and it can go from edge to edge of the building and top to bottom of the building. And so when you have a 2-hour concrete floor on one side and a 2-hour concrete floor on the other side and a gap in the middle, what we accomplish with this series of educational components that you're going to see here is how we address that gap opening in the middle and make it fire rated and performance for function for movement, for whether it's thermal or wind or earthquakes, things of that nature. So we're filling that void in, making it structurally sound, making it fireproof, smoke-proof, things of that nature. So that's just where we're headed. So when you think about joints in buildings, you might think about other things besides a typical expansion joint application. What you see here in the picture on the left is a curtain wall or perimeter wall joint application. It's where the concrete floor meets an exterior wall component. The concrete might be rated, the exterior component might not be rated. They put a fire stop system in place that may be mineral wool, some kind of a spray. And so how's that different from an expansion joint opening? Well, the big difference is the requirement for movement in these systems. So most of the fire stop type of linear joints, which could be curtain wall or header wall or bottom wall or something like that, control joints, they move very small amounts. From 0% to maybe 5 or 10%, 12% is a pretty high end movement. But expansion joint cover systems, these types of assemblies we're talking about, they really started their movement at 25% plus and minus movement, which is at least double what you normally see in fire stop systems. But generally speaking, 50% is by far the most common plus and minus movement, which far exceeds that. And then many of them in seismic zones are 100% movement. So a system that is designed for 12% movement will fail, like you see on the picture on the right, in the process of movement when you need something in excess of what it was designed for. Okay, so how do the codes and the standards and all that stuff relate to this? Okay, so International Building Code Chapter 7 and the Fire Code Chapter 7 and NFPA Chapter 1 and 101 and Chapter 8 also, they all address this. So in this chart that you see on the left-hand side, there's a type of joint. So the HW, BW, head of wall, bottom of wall. The blue line is what we're going to be talking about today, the floor-to-floor, floor-to-wall, wall-to-wall, wall corner applications. Below that is curtain wall, perimeter joints. Below that would be like penetrations for fire stop, like where you run a plumbing or electrical or something like that through an opening. It's not really a joint at all. The building codes that are associated with that, IBC 715 is what really governs all of the joint applications, and IFC 704. The test standards you can see in the head of wall, bottom of wall, and in what we're going to cover in expansion joints are the same. The test standards UL 2079 and ASTM E1966. We'll dive down that a little bit deeper. I'll go to the far right. The inspection standard is the same as well. We'll go into that in pretty good detail, but ASTM E2393 for joints. Here's where it separates. In the architectural specification, there's two different specifications, one for fire stop, which is the 07800 series. So you see here 078443 for different kinds of joint openings. And you'll see 079500 series, 079513 in this case, for expansion and seismic joint openings. So how significant is that? Well, what that means is an architect that is looking at fire protecting compartmentalized design in a structure writes a completely different set of documents for the expansion joints than they do for any other fire stop application. And primarily the reason for that is because the movement that's required, and a lot of, in most cases, there are some structural elements along with this. So there's cover plates and metal things, things like that that resist wind uplift or a pedestrian crossing, like people walking over it or cars driving over it and things of that nature. So these are often bid completely separately. So fire stop joints in all the building may be a completely different bid package from the expansion joint bid package. So this can be tackled by two different contractors. It could be the same contractor with two different contracts on the project. There's a lot of difference in there, and that's because there's significant application differences. So we're going to look at those today. IBC 715, fire resistant linear joint systems. A joint in or between a fire resistant rated wall, floor, ceiling assembly must be protected by an approved fire resistant joint system, and it must be of a time period that is not less than whatever the construction around it is. So if you got a 2-hour rated floor on both sides, you have to have a 2-hour rated system spanning that gap joint opening. And the IBC also addresses installation. So systems and materials must meet what the manufacturer says they're supposed to. So you're supposed to abide by the manufacturer's instructions. Fire resistant joint systems. This is a big one. This goes from the code to the standards. So this says, the code says 715.3.1, here's how you deal with fire resistant joint systems. And in that it says it must be tested. Anything you put in that structure should be tested to ASTM E1966 or UL 2079. And then it also has another reference for joints in smoke barriers, which we're going to address that, but that has a different kind of a rating. We'll take a close look at that. It's called an L rating. Air leakage, that's what that L stands for. So what's the difference between a smoke barrier and a smoke partition? So we're going to look at the words barrier versus partition. This is important information. If it has the word barrier in it, it's a structure that is going to be fire rated, even if it's called a smoke barrier. A smoke barrier has at least a minimum 1-hour fire rating, whereas a smoke partition is only smoke rated, and they're handled outside of that UL 2079 ASTM E1966 reference. They can be handled through other kinds of ratings like an ASTM E90 or other kinds of applications that are related to the smoke barriers. So smoke barrier, smoke partition, different things. Smoke barrier, same as a fire barrier. Smoke partitions, only smoke. Okay, so the International Code Council and the International Fire Council 2021, International Fire Code, sorry. International Fire Code is in lockstep with the International Building Code, right? They say all the same things, but what you see in blue down there at the bottom is in 704.2, is if a system needs to be repaired. So if it's damaged or updated or whatever, you have to meet the current standard. So that's a big deal. So if you have a damaged fire barrier, or you're renovating and putting in a different system, cleaning up the area, doing, renovating and making a new room out of it, or new structure out of it, or new process, it has to be brought to current code. That's a big deal because you're not just trying to put a new fire barrier in. You may have to have new construction. You may not be able to even find, maybe the old system that was installed was discontinued. You might not even be able to locate it. So you have to bring all that up to current code. And so we'll see references with UL, Underwriters Laboratories, and Intertech Laboratories. And they are in pretty good lockstep. They are in agreement with each other in how these processes work. So UL combines three methodologies: material, movement, and fire resistance. And ASTM does that in three different places. E119 is the time temperature curve. That's inside the UL 2079, but the ASTM is the time temperature curve. So how hot and how long do these things burn and have to resist fire in a test? ASTM E1966 is the overarching segment that says when you're going to deal with expansion joints and fire resistive joint systems in a building, this is what you need to address. And then ASTM E1399 is specific to the movement, expansion and contraction. So the primary document for ASTM is E1966, and it references E119 and 1399. And UL addresses all three in one document. So how does a manufacturer show that they have met these kinds of standards and they meet the codes and the test standards? A document called a listing is produced from the laboratory, so it could be from UL or Intertech or any other nationally recognized laboratory. And so there's usually pictorial evidence of the design of the structure. It shows the materials that are construction. It shows the fire barrier material. Any other references that need to be placed in there, like joint covers or any other kinds of things like that. Those are all listed in this documentation. And this document states it meets certain kinds of movements. It gives you any alternative kind of applications, like different kinds of covers or different kinds of wall construction or something like that, that was also allowed in addition to what you're seeing here. And then it also has an audit system for the manufacturer's facility. So these laboratories go out and look at the manufacturer's facility once a quarter or whatever, and they say, yeah, you're doing it the right way, or no, you're not using the right kinds of sources, or whatever it is. And then there's a quality control measure. Could be ISO, could be some other kind of system being used at the manufacturer that's stated in that documentation to ensure that they have the quality process in place. So when you get to the inspection side of the business, we're looking at NFPA 1 version 2021. It says basically the same thing, ASTM E1966, UL 2079. It also addresses the inspection standard that is used most often to inspect fire resistive joint systems, ASTM E2393. That system was mandatory in approved jurisdictions as of 2015. It's not mandatory everywhere. Not all jurisdictions have accepted it and moved to the different, they take time to go through the different code adoptions, of course. But what we have is, in this, we have a mandated system that is well thought through. And if you don't have a system in place, it's still the best guide to use to be able to go out and do an inspection. So whether or not it's required, if you're asked to do an inspection for fire resistive joints on a project, whether it's inside the code adoption or not, it's still a great guide to use. And so it covers the types of buildings, and essentially if it's a high rise or high occupancy. So high rise, high occupancy, it's going to be included in these kinds of structures for these types of inspections. So risk category 3 and 4 are anything high occupancy: public assembly, elementary schools, education, adult education, hospitals, prisons and jails, where you may have some utility operations, or anything that's going to have some kind of impact on the public if something happens to that in a fire. And then it also extends one more level to essential facilities. So what this group is anything that supports those, like first responders, firefighters, police, medical, emergency, things of that nature. Or if it is a shelter of some kind, like a hurricane shelter, a tornado shelter, or bomb shelter, or whatever it is, those kinds of things that are meant to protect the public in some kind of way are also included in there. So you have a pretty large group of items that are used that use this type of inspection system. So how do we know that a third-party inspection is credible, right? Well, one, they have to be an independent agency, so it can't be a part of the general contractor, the architect, the manufacturer, whatever, contractor. It needs to be an independent agency aside from all those. The personnel has to be approved, the agency has to be approved. To do special inspections, the owner has to have this, so if it's required and mandatory in their jurisdiction, the owner has to pay for it, put that in their budget of their building. And then the inspectors have to have qualifications. They have to go through some kind of testing and have some type of credentials. Like you can get that through the International Fire Stop Council, through training. There's probably other sources out there, professional engineers, things of that nature. Those folks are qualified to do those kinds of inspections. So when you're going to do this kind of third-party inspection, you use this ASTM E2393 standard. So what do you do with this standard? Well, one of the things that you do is that you randomly witness a minimum of 5% of total linear feet of each type of resistive joint system installed. So if you've got a floor system, a wall system, you may have different sized joints, you may have different construction. You may have one floor that's a flat deck and one floor that's a corrugated deck and one floor that's post tension concrete. You can have precast tees, you can have, so if you're in those different kind of environments, you would look at those different things. You could have a gypsum wall, you might have a 2-hour wall and a 3-hour wall. You can have a block wall or concrete wall or any number of things. So you need to do something 5% representative of each one of those kinds of systems. And then there's some post-installation inspection where you inspect a portion of up to 500 linear feet of these different kinds of systems that you're looking at in the structure. So practically what I see most of the time in a project is that a contractor that's installing the system will install a fire barrier material, and then there's also generally some type of joint cover system with it, maybe metal, rubber, whatever, any number of things. But they put that fire rated system in there and they call for the inspection because they know if they know that there's going to be an inspection, they call for the inspection while the material is exposed, because you can see the labeling of it, you can see the fastening of it, you can see all kinds of things that we're going to go through as we go through here to make sure that that is approved. And then once the inspector has approved that, then they put their joint cover on. And one of the reasons that they do that is because some joint cover systems, metal systems or whatever, elastomerics, they can be fastened in a way that if you dismantle that, it could be damaging to it. Or, these systems don't lend themselves very well, these fire barrier systems don't lend themselves very well to, some type of demo view of this. Like you can with fire stop, you can cut a little section out and then look at it and measure the thickness and seal it back up, but that's not very easy to do in a pre-engineered, pre-manufactured factory fire barrier system. So it's very hard to do that kind of destructive testing on those systems. So generally speaking, put the fire barrier in, get an inspection, put the cover on, and then move on to the next section. Fire testing. When the factories do fire testing according to this ASTM E1966 or UL 2079, they test for different things. One, they test for fire, which is visible flame, right? So that picture right there, you can see a fire poking through on the right-hand side there. So that would be a visible flame. So if that was on a tested component, that would be a failure of that component because you see visual flame. There's also a thermal temperature rise that tells you certain temperatures, depending on the hour degrading that you're working with, and the ambient beginning temperature. If it goes above that in either a single thermocouple, which is basically a thermometer, that those little squares that you see there, there's a temperature gauge there in each one of those, or an average over the bunch. If it exceeds the test standard, then you have a failure there. And then there's an L rating, which is generally a separate test from these because they're done at a different temperature. They're done at an ambient temperature and a 400-degree temperature. That L rating is optional in these, but it's required for smoke to get a smoke rating. So in these testing requirements, if you look at ASTM, they notify all these different kinds of joint cover systems. So the fire barrier is one component, the cover is another, and that could be metallic, compression seals, preformed seals, elastomeric, all kinds of things in there. It can be stainless steel foils, it can be any number of things. The direction that they test this movement in is referred to as X. That's perpendicular to the joint. So that's a joint expanding from its nominal state, which is what it's drawn at on the drawings, say 2 inches or whatever, expands out to 3, that would be a maximum open, expands down to 1, which would be the minimum close, and back to its nominal 2, that would be a plus or minus 50% system. There's calculations in there, there's definitions of what those look like, definitions of what a full cycle is, and then there are definitions that say how many cycles you have to do to pass this test. ASTM has a class 1, 2, and 3 that looks just like this chart that you're seeing here. 500 cycles going really, really slowly, 1 cycle a minute. For thermal, class 2 is wind sway, which is 10 times faster. Class 3 is seismic, which is 30 times faster. So it's very, very quick. And UL 2079 adds a class 4, which is sort of a hybrid of that group. And they say, well, if you'll do 100 cycles at 30 and 400 at 10, we'll give you a freebie on the thermal and kind of go from there. And that's what most manufacturers do in the testing. So what does the test apparatus look like? Number 1 on the left is for cycling. So what normally happens is there's an apparatus that can move back and forth, and you fasten your fire barrier and your metal cover plate to it, and this thing expands back and forth, and it moves this system 500 times through its full range. And what it does is it fatigues the system, it tests splices, it checks to make sure that it has the full range of motion as required, and if it survives that test, then it gets to go to the furnace and get burnt. That specimen that was cycled goes straight to the test and gets burnt after it's been fatigued. And so it can be in a horizontal oven or it can be in a vertical oven, depending on if you have a floor, wall, roof, whatever kind of application. And then if it is a wall system, then it gets also a hose stream. So a fire hose is shot at it at a certain PSI for a certain period of time, depending on the size of the joint, the hourly rating, things of that nature. And so it's meant to be a structural test and a test to make sure that water doesn't come through, because if water goes through, typically smoke or something like that would go through as well, and so you have other kind of issues there. So it's a pretty rigorous test. Hose streams are not done on floors in joints, but they are in fire stop. They are in penetrations. They are done in the floors and the walls. So both penetrations and joints in fire stop applications have this hose stream testing, but floor joints do not. So what do these things look like? So if you're looking at a joint cover system, right, you've got maybe a draped looking thing, that U-shaped piece in there. You got concrete on each side and maybe a metal cover plate on top of it with some screws and stuff, right? And you can have that with elastomeric seals. You can have it with stainless steel foil covers. You could have it, like on a roof, you might have a bellows roof that could be made of EPDM or silicone or PVC or any number of things, TPO roofing or whatever. So you got all these different kinds of combinations that would be the fire rated barrier, the joint cover, and the construction. That whole thing is the assembly. The barrier, the cover, and the construction, that's the fire rated assembly. So there's different hourly ratings. Most of the time they are from 1 to 4 hours. 2 hours is by far the most common. 3 is pretty common. 1s and 4s are not as common. There are some 1s in certain applications, like those smoke barrier walls. And then we make sure that we meet the code in testing compliance using one of these factories. It could be UL, Intertech, in this case FM Global as well. So what do these things look like? Well, there are different types. So when you look at smaller joint openings, which are the most common in the US, most of the US is a thermal expansion and contraction zone. So if you get away from the coasts, you get away from the seismic zones, most of the rest of the US, the joints are going to be anywhere from 1 to 4 inches wide, nominal, and you're going to move plus or minus 25 to 50%. Those may have systems that are made from mineral wool and sealants or other kinds of things like that, or textiles that are using intumescent materials and some sort of draped covering or something like that that goes along with it. So maybe there's an aluminum foil scrim or stainless steel thin foil sheet, or maybe there's a textile high temperature fabric material in conjunction with an intumescent material to make up those kinds of systems. But when you get into these other 4-inch joint kinds of sizes of systems, the smaller joints in that same family, you see a lot of non-mechanically attached systems. So they don't use screws or fasteners to put them into place. They are friction fit into the opening. And so they may be a draped system that has spring loading. They may be a series of intumescent and foam blocks. They may be foam seals with silicone coatings. There could be any number of these drape systems with some hybrid components. But the main idea is that they do not require mechanical attachments to function. But when the joint gets above 4 inches, 5, 6, 8, 10, 24, 48 inches, or whatever else, they generally go to some type of draped insulative system with a pretty hardy exterior surface, which could be anything from meshes to foils to high temperature fabrics or combinations of all of these, and they all have some kind of insulated blanket material inside of it. So they can be pretty robust. So one of the things you look for in these systems is when you put this combination together, does it actually fit inside the opening or the area, the space that you have to work with the joint? So that left-hand picture, the fire barriers draped down below the bottom of the concrete, that's the way it was tested. That's perfectly fine. And as long as you have room to fit that in there, then you're fine. Maybe your ceiling plenum was down below that or whatever. It's all good. As long as it passes the test and that's the construction, fine. The center picture is a barrier that's contained inside a structural concrete area, and then in the middle, that's the middle two systems, and in the right-hand system is a typical fire-rated wall, 2-hour gypsum assembly with a barrier contained inside that opening. So they don't always all fit in there nice and neatly. Sometimes they are bigger than the system and you have to build them out, but those instructions are built into the manufacturer's instructions. So when we get to the construction component of it, there's some intricate items. So I'll tell you about concrete first. So a lot of systems are tested with, say, a 4.5-inch thick concrete slab, lightweight, normal weight concrete, whatever it is. And so if you have 6-inch slab, fine. If you have a corrugated slab, that may or may not meet that criteria. So it depends on what kind of construction. If you have a 6-inch requirement, so you tested a 6-inch thick slab for a 3-hour floor system, and somebody wanted to put that into a 4.5-inch 2-hour system, probably would not be okay. You probably had to have an engineering judgment or find a different system or whatever that is, because you have a mismatch. You have a 6-inch requirement and a 4.5-inch field condition, and that's a no-go. If you have a 4.5 requirement and a 6-inch field condition, typically speaking, that's okay. So this is walls that we're looking at here. So the left-hand picture is a gypsum wall. If you look at the right-hand part of that, there are 2 layers of gypsum that go out to the edge of the stud. That's where the edge of the expansion joint opening starts, and it would look a mirror image to that to the other side. On the left-hand side, you see 2 layers of gypsum, but one of them is staggered back to allow space for an expansion joint cover system to be placed in that opening. If it was tested that way, it would be no problem. But if it was tested with a joint cover on the surface of 2 layers of gypsum like the right-hand side, and you installed it in a system like you see on the left where you've got gypsum that is not protecting that opening, then you may not have a system that is approved for use. It may not meet the standard, it may not meet the test criteria or the listing. On the right-hand side is something that's really commonplace, and that is the top picture shows some gypsum, drywall, whatever, run to the edge of a metal stud, and there's no drywall on the interior throat of the opening of the joint. But the bottom picture has 2 layers of drywall and 2 layers of drywall on the interior throat opening. So what's the difference? If you have a system that is tested like the bottom, where there's gypsum in there, you cannot install it like you see in the picture in the top. That would not be okay to do. If you have a system that is tested like it is in the top, where there's no gypsum on the inside, but you had gypsum in the throat opening, it would still be okay to use because you have no requirement to have gypsum in there. So adding materials that are non-flammable generally do not take away from the performance of the system. The next step is splices. So what do you do? These things are not made infinitely long. They're usually in 5 or 10 foot long lengths for most fire barrier systems. Well, the test standards state that you have to test this with an inline splice. So a butt splice or a lapped or folded splice or whatever those are, that's part of the test requirement. So when you cycle this thing in a machine, it's cycled with a splice in place. And when you put it on the fire test furnace, it is fire tested with a splice in place. So that is part of the assembly. So you have to do the system the way it's shown. However, when you go from a horizontal to a vertical change in direction, there are no test standards related to that change in direction. That is just simply noted as whatever the manufacturer's instructions say to do to connect these systems. And part of the reason is it's difficult to do a horizontal and a vertical test in the same oven. This oven's just not made to do that. The other is you can have a variety of differences. You could have a whole range of different floor systems and wall systems in combination. So you could have a pretty infinite types of arrangements in those. Whereas in the linear splice, it's going to be the same product to the same product typically. But here you have a change in direction. So it just notes in the standard, whatever, just follow the manufacturer's instructions. One thing that's worth noting in this is that if you have two different manufacturers' products on a project at the same time, if one was supplying the floor and one was supplying the wall, there's no test standard that says that that's not okay to do. But you do have the area where they meet, where it says, you have to have some sort of recommendation. So that can be worked out, but it would not be against a code. However, if you did the linear splice version, you typically would not have one manufacturer to another one in a linear splice. So we're going to look at some project examples. When you're looking in the field and you want to see what a fire barrier should look like, you look at sealed edges, right? You want to make sure that those are clean and neat and tight so that you don't see gaps and openings. When you look along the linear length of this thing, this is a pretty long piece. Here, there's a splice there. You can kind of barely see it, but it's two screw heads are close together right there. There's a splice there. If that looks nice and clean and it's all packed together, and you're looking at the manufacturer's instructions and it says, yep, this is the way it's supposed to be done, then this is a good one. This is a good example of what you should do. Another good example is when you go from a horizontal to a vertical. If you see clean lines, tight, it's been sealed up, and it meets the manufacturer's instructions, chances are excellent that you've got a really good system in place here. If you've got splices and changes in direction, as long as those things are sealed up and neat and they meet the instructions, you're in good shape. However, when you get into the field, sometimes you see different things. So on that top right-hand side where you see all that red material there, that's typically a head of wall fire stop application. But when you move your way over to the right, you can see a big opening in the wall there. That's a big expansion joint gap opening. Look what's going on here. So right, you got a big expansion joint gap opening and you've got a huge piece of conduit going in there and turning into that opening. Those are not okay. You're not supposed to have this. Called no man's land. You do not put things inside the joint gap opening because the joint gap is designed to move. And if it moves, it's probably going to compromise whatever's inside there because the building's not going to stop moving. It's going to probably damage that pipe or that electrical or whatever's going on inside that opening. And then when you look further up, you can see that the joints different sizes. In the ceiling and the wall are two different sizes. So you could call to attention, hey, this probably needs to be remedied some way in order to make sure that these things all align up and fit properly. So maybe one needs to be closed down, or it needs to be opened up, or whatever you need to do there. But that'd be an area that you want to call attention to. When you see these installations in place, if you look at the left-hand picture, it's got the two arrows. The top arrow, there's a piece of conduit going across the joint opening. Again, that is not supposed to happen. That shouldn't be there. There's a number of reasons. Even if it's flexible, it could be in the way of the fire barrier. It could simply just get damaged because it may not be made for the kind of movement that are in place there. So that's usually a bad sign. And then the bottom arrow. So most manufacturers are going to show you in detail a nice clean transition from a horizontal to a vertical application. So if it's just mashed together and shoved up there and all wrinkled, then there's probably gaps and openings. And if you shine a flashlight up there, you can probably see through that. Then you're not likely going to have a good fire tight kind of installation. So that's probably one you'd call attention to. The middle picture has got separated splices. So these splices should be tight together and they should be sealed up and all that. And so if you see those kinds of gaps, obviously there's going to be some kind of an issue that needs to be remedied in some way. In the picture on the right, so that big square block looks like a railroad tie. It's actually a piece of mineral wool that has been stuffed into the joint opening, and this could have been in place for a long time. There's a kind of an underslab mounted fire barrier in that silver shiny part there. That's a manufacturer's fire barrier, so that was designed for this application. But somebody just stuffed mineral wool in there. Probably what happened is that mineral wool was nice and tight and stuffed in there and butted up and looking good when they left. But the building does what it does, and it moved around, and mineral wool doesn't bounce back very well. That's why you see fire stop sealants and things like that attached to them in most applications. But they're just not designed to move the way these buildings move. And so what happened? It fell out. It just fell out of place. And so that needs to be remedied and taken care of course. Another one is, from above, when you're installing a system, you may or may not be able to see underneath it. So the left-hand picture, you're looking underneath at this fire barrier that's been installed from up above, and they may have damaged it putting it in. They may not have gotten the screws in place right. Any number of things could have happened, but you can see that this thing has come apart. Right? It's supposed to be wrapped up nice and neat in that kind of gray packaging, but you can see the insulative material just hanging down in there. So that is not going to be an okay installation. The right-hand picture is from above the floor, looking down at one installation, and you can see that the fire barrier was just shoved in place, and it's got a big gap there. Obviously, that's not going to be sealed off and smoke tight and heat tight and all that sort of thing like that. So we call attention to that. But then it just gets downright ugly. So who knows, right? In a fire rated joint application, they could have run ductwork like in the left hand picture. They could run ductwork in there and said, hey, listen, I got a great big wide opening here. Just works out wonderfully. So they just shove it full of whatever, and there's no fire barrier system in there. And then they try to shove some pieces of mineral wool or whatever else they have in there, and there's large gap openings. It's just really ugly situation. So obviously that would be one to call attention to. The second picture from the left, somebody just cut the fire barrier open and put a pipe in there, plastic pipe. So that is not designed that way, most likely. And so you'd want to call attention to that. They may have been thinking they're cutting into ductwork or any number of things, but that is a bad application, of course. The second picture from the right is a conduit in the joint opening, and the right-hand picture is a whole series of mechanical assemblies inside the joint opening, and those are problematic. If that building moves like it's designed to move, what's going to happen is those utilities are going to get compromised. They're going to get crushed or broken or something like that, and some IT guy somewhere is going to be in some person's office, and he's going to say, my computer doesn't work anymore, and he's messing around trying to figure out what's going on. He has no idea that all the electrical is crushed down in the basement because it was designed not to be put in this way. So water is bad for fire barriers, so we try to keep them dry. If you get water in there, it can do a lot of things. One, it can compress the insulative materials and take the insulative value out of it. So if you lose those air pockets, they get squished together because they get wet. They don't rebound, and so it just doesn't work out quite well for those kinds of, if they get wet, those kinds of barriers if they get wet. Another problem is mold. If these barriers get wet and they're not taken out, replaced, or some barriers can be taken out and dried out, but if that doesn't happen within about 3 days, then mold can grow on just about anything. And so you just look for that dirtiness, and that dirtiness look most of the time is some kind of growth happening in those insulated blanket areas, and so that's problematic, and those have to be removed for sure and replaced. So before we go to questions, I'll kind of summarize what we just discussed. So you want to compare the substrate conditions, you want to look at the construction against the manufacturer's installation instructions and the listing data. So you want to make sure that the right kind of construction is in the right place, the right kind of barriers in there, and it's fastened and connected together the right way, according to that document that comes from the lab for the factory saying, this is how it was tested, this is how it should be done. A solid substrate with no voids is critical for securing the barrier in place. So what you don't want is weak construction, spalled out concrete, very flimsy metal backing behind chipboard that flexes and bows out of place so that you can't get a good firm connection. Make sure you consider the fire barrier is the product, but it's also part of the whole system, which is the joint cover, fire barrier, and the construction. And when you're inspecting, look for continuous contact with the substrate. Make sure that you have the correct attachment. And there's a lot of information in these listings that tells you how many inches on center your fasteners need to be, or what kind of adhesive should be used, if it's spray adhesive or epoxy or whatever that's used to seal, or silicone or whatever is used to seal these kinds of systems into place. Just make sure those are the right things that were used in there. And if you take care of that, then you'll most likely be okay in your inspection. And so I want to say thank you to a lot of folks that put this together. Of course, the International Fire Stop Council for providing all the means and everything for us to have meetings and get together. The Expansion Joint Council is a really good, proactive group. They put a lot of work into this presentation. And so thank you to folks from, of course, Balco, Inpro, Sika, MCL, and Watson Bowman, and Construction Specialties. A lot of good inputs from a great set of team members that helped put all this together. Of course, you can contact me if you have any questions after this. You can have a chance to ask questions in a minute with Aaron. But you can contact me, or you'll contact the International Fire Stop Council at firestop.org. They're at their website, or info@firestop.org is their email. Ask questions. We would be more than happy to help.